And looks like we're live. Okay, good. Welcome back, YouTube, to this video. So in the last video, we're going to continue our discussion on OpenFOAM, specifically the snappyHexMesh bit. I just want to quickly wrap up the add layer part before I move on to other more interesting parts like turbulence modeling. Okay, so I know I kind of promised more complicated meshing, but that will come later after the turbulence modeling part. Start to deal with different shapes. So now it's just a pipe case, so you don't want to overdo it. Might as well do the more complicated meshing parts later on. But anyway, just want to summarize the layer controls bit. So we sort of saw that separating this layer addition out to be done after auto patching may not be the best idea, because apparently it will not resolve the issues. I mean, it will have some sort of error, and the thing will not be able to resolve properly the layer addition bit for some reason. Okay, I have not figured it out as of this video yet. If I do and I have time, I can post it up, but as for now, this is what I have, and this is what works, is that you have this internal mesh that's structured like so, and we do the auto patching part later. Alright, we do the auto patching part later, and we so-called add these layers a little while later. Alright, I mean, I guess there are ways to circumvent this, but I'm not going to talk about this now. Just want to quickly say the final workflow. So we are not going to run snappyHexMesh twice, and you kind of turn on the dictionary, turn on the add layer bit after your auto patch, because that doesn't work. Okay, so what happens to work is this, and basically all you have to do is just to turn the add layer feature on, and what you need to do is after that just go to your layer controls, make sure you are selecting the right patch. I put the wildcard here to say that on every patch I want to add end surface layers of three surface layers. So, and I turn on relative sizes, which I kind of explained a bit in the last video. I kind of roughly went through expansion ratio. Okay, that should be quite intuitive enough. Just note is going from one cell to the other, not the first cell. It doesn't compare the first cell and the final cell. It's one cell after the other. Okay, final layer thickness, we explained that. Minimum thickness, you can't sort of explain. The rest of these I will not touch for the time being. Okay, I'll not touch it for the time being, because I kind of want to move on to more turbulence modeling. Okay, so right, let's do some house cleaning first. All right, let's go to system, and we'll remove the snappy add layers dictionary, because that doesn't seem to work, and we have our auto patch mesh gen. Okay, and this is basically what this thing looks like. All right. Okay, I can use a bin bash. Sometimes that helps to make it work better, for especially if you have a lot of bash scripts. Okay, but anyway, we executed these steps, and we have made a mesh that we roughly can start work with. All right, and that's a good thing. Okay, so now let's try running PimpleFoam on it. Okay, it should be able to run properly. Okay, it will take a while. Looks like a long while. Okay, so but anyway, PimpleFoam runs, and there is no issue with running PimpleFoam. As you can see here, I can just run PimpleFoam, and it will do the kEpsilon model for you. So, like I said before, you don't just want the kEpsilon model, because that's kind of boring, right? That's kind of boring. So yeah, not only that, I'm just starting to realize how many scripts there are over here, which I don't necessarily want to have. Okay, let me remove the continue run, because I can teach you how. I already gone through parallel running. I'll refresh memory if needed. Okay, let's see the all run semi-parallel. Now I want to see whether, okay, these are sort of useful. Mesh generation and mesh generation parallel. I'll get rid of the mesh generation. The parallel one I can sort of scavenge it later. To see what is good. Let's see the run bit. Yeah, this is just running the pimple foam. Okay, it's nothing big. Okay, run. And let's take a look at run parallel. I just want to get rid of some scripts. This is the decompose parallel part. I'll just keep that bit. Alright, now it looks a lot neater. Okay, so actually we can remove that all run semi-parallel as well. It's kind of redundant at this point in time. You can always look at the older ones if you want to take a look, the older scripts. Okay, so anyway, let's go to constant. Let's figure out how we can take a look at other turbulence models besides just k epsilon. Okay, so let's do pimple foam and list turbulence models, and this is what will come out. This will show you all the turbulence models you can use. Some of the most interesting ones, the most popular ones will be the kOmegaSST model and the Spalart-Allmaras model, as you can see here. These will require different variables for you to sort of use, and well, yeah, there will be some adjustments needed. There are lots of other models as well, but these are very popular. Why the kOmegaSST is popular is actually a hybrid between this kOmega model and the k epsilon model. It supposedly compensates for each of their weaknesses, and it's kind of a best of both worlds kind of blend. Spalart-Allmaras model is very popular with the aerospace industry, in CFD in aerospace anyway. This is pretty good because it's simple. There's only one variable you need to play with and calculate, and that's the Spalart-Allmaras variable that sort of works like turbulence viscosity. If you want to know more about this, do go and look at my turbulence modeling video series. I talk about the background and theory of these things, these models extensively, and you can find out more about these. Okay, so these are some of the most popular ones. The rest of these equations I'm not going to touch on as much, but at least want to show you how to do kOmegaSST and Spalart-Allmaras, as well as some of the equations you see here, the large eddy simulations, but we'll come to that later. Okay, so let's do first thing first. We can go to constant. Okay, and what we do is, now we are done with the mesh and everything, you can go to turbulence properties. So over here we can just type kOmegaSST. So kOmegaSST, and let's try running pimple foam. And let's do it on this side. Pimple foam. Okay, it's going to give us an error because I mistyped it on purpose. So what did I mistype? We are constant turbulence properties. If you notice that I put the kOmegaSST, I kind of didn't capitalize the O's. So that actually tells you, OpenFOAM, pimple foam in this case, will, even piezo foam, it will do that. If you are not sure about which turbulence models to use, how to type it, you can just mistype it as I did, and it will show you the list of valid entries. So these are the valid entries which you can just copy and paste or type exactly. So, oh shoots. Yeah, okay, good, it's still recording. I thought it's not recording. Okay, anyway, oops, I think I paused it for a while. Yeah, I was just wanting to check the OBS Studio, see whether it's working. Anyway, so we have kOmegaSST right here. kOmegaSST right here. And you can take a look at the list here. They'll provide you some of the stuff, the right models to put. How do you spell them properly? And that's all you need to do if you ever forget. So we'll just run PimpleFoam, and again we'll run into an error. Why? Because you see the method is not found. There are some things that are actually missing. What is missing actually? You look at this one. It says that the method not found in the dictionary fvSchemes. Okay, fvSchemes. You actually need to edit your fvSchemes and fvSolutions a little bit. So where do you go? Where do you go and find all these? So go to Foam Tutorials. Okay, go to Foam Tutorials and go to Incompressible. Do your grep command, grep-r, and you do kOmegaSST. Okay, what you will see is you will see some of it in SimpleFoam, you'll see some of it in PimpleFoam. Okay, and the one you will see is this PimpleFoam Wing Motion 2D. You will have this case here. So I'm going to copy and change directory to there, and I'll go and take a look at their fvSchemes and fvSolutions. But I'm going to go through the process with you, so I'll keep doing errors on purpose. So at least I'll show you how to write your own. Adjust the fvSchemes and fvSolutions on your own. All right. So what do you need here? We need this thing called wall distance. Okay. So we go to our own fvSchemes. All right. And what we need to add in is this thing called wall distance. Okay. Let's go and add in wall distance. And here it will say this method is mesh wave. Not going to explain too much of what that is. All right. The other thing is that you need to know k and omega needs to be solved. Okay, k and omega needs to be solved. So there needs to be an entry in this divergence schemes. So basically the fvSchemes discretizes, it converts the partial differential equation into a system of matrix equations. That is the idea. All right, that is the idea. Let's see how much time. All right, it looks like it's 13 minutes in. Sure, 13 minutes in. All right. So anyway, I have this entry for k, and this k is actually the same k whether you do k epsilon or kOmegaSST or k omega for that matter. And then there's also an entry here for omega, which should be there. All right. So what are the entries you need at least for kOmegaSST? So you can take a look at the schemes over here. You will see a time scheme given because it's PimpleFoam. You have gradient schemes, and you need to have at least all these divergence schemes. So you have phi and u, which is for velocity, phi and k, which is for the turbulent kinetic energy. Omega is for the dissipation or the turbulent frequency. Okay, so this is the turbulent frequency, and then you have this dive new effective deviatoric stress. I don't know how to pronounce it properly. I'm not pronouncing it right. Okay, but this accounts for the deviatoric stress term. Okay, which if you're not sure, you can do a quick Google, and I have it in my turbulence modeling part. Deviatoric stress is it's sort of the kind of it's like pressure, the vector form of pressure without the hydrostatic pressure bit. That's putting it, yeah. But whatever it is, I mean, in OpenFOAM you should just have this entry here. So that's here. Then we take a look at the Laplacian schemes. There's an entry here. over here there is Gauss linear limited corrected, and this one says it's orthogonal. I would go with the limited corrected scheme because orthogonal, this kind of orthogonal mesh, this is actually for meshes where, you know, where our mesh is like block mesh, you know, block mesh, and all the squares are kind of orthogonal to each other. All the cells are orthogonal to each other. Then you kind of use this scheme. Otherwise, you should have some form of correction. So limited corrected. So this is one form of correction. You don't have to use this particular scheme, but this is definitely better than orthogonal. And likewise, over here we should have the SN gradient scheme, surface normal. SN stands for surface normal. So the surface normal gradient scheme should also be corrected, unless it of course gives you stability problems. So let's try running PimpleFoam again. Alright, and you'll find again there's an error because there'll probably be errors. Okay, maybe no errors this time, because actually there may have been things missing in FV solution, right? VI FV solution. Normally, that if you are using a K epsilon model, this omega entry is missing over here and over here. But you know, if we have these entries here, then no problem. It will solve, and this will be also true for these relaxation factors. I have all of these here, and apparently you have the omega entry and you have the K and epsilon entry. No problem. Alright, so we can actually run the case, no problem. Yeah, we can run the case, no problem. Okay, so this is how it's run. We can also run it in parallel. So I just do a decompose parallel and you'll go into 4 processes. So all I have to do is to type MPI run. Okay, just listen. I mean, if you're not sure how to run in parallel, just off command line. You need to use this MPI run. NP stands for number of processes. So here we have 4 processes, processor 0, 1, 2, and 3. Okay, MPI run 4. Then you need to put PimpleFoam, okay, parallel. This is the full command you need to use to run PimpleFoam in parallel after you have the decompose. You can of course put the N here if you want to sort of you want to sort of have this running in the background, but I don't want to, so that in case, you know, I want to stop it halfway, it's a lot easier just by pressing Ctrl C. Okay, so this is how we do it. Okay, so if everything works well, this should be the output, and you'll see now it's running in parallel perfectly. Okay, so I just needed to drink some water there. Yeah, basically this is how we run a kOmegaSST case. The idea is you try and put in the kOmegaSST model using the method I kind of shown you, and basically you just keep running, check back and forth, see whether, you know, this model actually works. Okay, whether this model actually works in the turbulence properties. Of course, you can actually edit a lot of the constants in there as well. Okay, so for example, let's say you wanted to change this thing called alpha K1. You may not be sure what it means, but if you want to have that, yeah, if you want to have that, you can do that. So I can go to constant turbulence properties, and I say alpha K1 is some value like 500. It'll probably be wrong physically, but this is just how to show you how to get it done. So this is what alpha K1 is, 500. Alright, so for example, if you ever wanted to do that, you can. Okay, so let's do the MPI run again. So you see alpha K1 here is 500. Okay, this is how you kind of edit some of these constants if you so wish to. You just do it in your turbulence properties over here. So I'll just leave it in comments in case you ever want to check. Okay. I'll just leave it in comments. But yeah, basically this is how you do your kOmegaSST. Of course, we can do similar thing for Spotlight Armorous. You'll just need to make a few more entries as we did before. Again, if you don't know what entries to put, you need to put, just go straight to the Turbulence model. I mean, you can go to the OpenFOAM tutorials. There will be example cases where you can check which entries you need to key in. Okay, so I'll stop for this video. Thanks for watching. I'll see you guys again. Bye bye.